Welcome to the third part of the series in compounding cream formulations. In this part 3 video, we are going to look at specific examples and the formulation as well as compounding principle. If you have reached this stage, that means you have watched video 1 and video 2. Let's look at a recipe or a formulation with a soluble powder. Now on screen you have cetrimide BPC cream. Now these are old recipes, but they do demonstrate a principle, which is what we're carrying across in these videos. It requires 5 grams of cetrimide, cetosterol alcohol, which we will know by now, having watched video number 2, that this ingredient is an emulsion stabilizer. It thickens the cream and adds body. Now 50 grams. Liquid paraffin would be the oil phase and your emollient in the recipe, and we need 500 grams. Water, FBC means freshly boiled and cool, but in the context of making cream, we know that is 60 degrees, 60 to 65 degrees, because this is the fusion method. So don't be disturbed by the FBC abbreviation here. Now, the tricky thing is, cetrimide in this recipe is the emulsifying agent. It is also the active ingredient, so it's playing a dual role. How would you make this? The cetrimide would first be integrated with the aqueous phase, whereas the liquid paraffin would be integrated with the oil phase, which is the cetosterol alcohol. Remember, when making creams, you separate the oil phase from the water ingredients. Now, once you have done that, you've created your melt on the water bath. We have the liquid paraffin. They're all merged nicely at 60 degrees. The water phase is also merged nicely at 60 degrees and also contains the dissolved cetrimide. Now, this is the trick. Divide your water into 2 portions. So 444 grams would have been needed for this recipe. So mentally allocate, for example, depending on the solubility of the cetrimide, use the amount of water to dissolve it in a beaker that you know will dissolve it in a beaker. Now, reserve some of the hot water to rinse the beaker to make sure that when you transfer the dissolved cetrimide into the melt, which is the beaker, the crucible containing the cetosterol alcohol and liquid paraffin, you want to make sure that you reserve some of the hot water to rinse the beaker to recover all the cetrimide, that nothing stays back. So for the water, reserve some for the dissolving of the cetrimide and for the rinsing of the beaker that was carrying the cetrimide. Once you have successfully merged all the 2 phases, with this formula, remember now, 454 grams of hot water, you can wait. If this is a large batch on a small lab scale, remember 1 gram of water is equal to 1 ml. And so you could actually, if you're doing a small scale formulation, for example, you're scaling this from 1,000 grams to say 20 grams or 30 grams in the lab, you can actually use a syringe to make it, the water will not be too hot to destroy the syringe. You could actually measure your calculated water, right? So once you have done that, that's the formulation for a soluble drug. Let's move on to an emollient cream, formulation number 2. Now this is aqueous cream BP, which has been modified, the APF version, to include glycerol, 5% glycerol, right? The chlorocresol is the preservative. Take note, it's 100 milligrams. I think it's 0.1%. That would have been in the formulation, because here 1 gram, this formula adds up to 1,000. So if it's 100, that's 0.1%, because percentage is out of 100. Now, bear in mind that chlorocresol is not very soluble in water. When you read your Martindale pharmacopoeia, it says 1 in 260 water, and we know that a temperature is not mentioned, so they are referring to room temperature. Now, if you should read the Martindale carefully, it says more soluble in hot water, but guess what? The melting point for chlorocresol is 63 to 66 degrees. So we advocate that you make the solution with chlorocresol with water not exceeding 60 degrees. And so this is where your thermometer is really important because you do not want to destroy your active ingredient. No, you would make the cream similar to cetrimide. Why? You dissolve the chlorocresol in the water phase and leave some of the water to rinse the beaker that is carrying the dissolved chlorocresol. Now, because we're doing this on a small lab scale, you will probably won't have a quantity of chlorocresol that is weighable. So in the pharmaceutics lab, we normally make a chlorocresol triturate. The triturate is used using the solubility information. If 1 gram needs 260 water to dissolve, then X of what we need X amount of water. You set up your ratio and proportion, do your calculations, and you use the solubility as per Martindale. However, we will be using hot water maintained at 60 degrees, and chlorocresol needs time to dissolve, so you may have to rest it on a steam bath and make sure that the temperature does not exceed 60 degrees. Now, once you have made your chlorocresol triturate, remember, you're going to need time and keep it covered. So put a watch glass over the beaker that you'll be making your solution in. This is the time when you review your calculation for how to make a solid in liquid triturate. Now, if we're using the APF formulation, remember that this is weight in weight. 5% weight in weight means 5 gram in 100 gram of cream. Now, for ease of measuring, because it's a viscous liquid, you can use the density information, which is here on screen. 1.26 gram is equivalent to 1 mil, right? So you can actually calculate the amount of glycerol you need for the recipe, use a syringe to measure, because the density information allows you to convert the grams of glycerol that the formula asks for into mil. Now, these are simple things that you have to pay attention to when making your creams. Now, let's look at a formulation with insoluble powder. This recipe, I think, was taken from one of the older Martindale, like, for example, the 29th edition. The older Martindale pharmacopoeias has a lot of recipe. The newer Martindales are more clinically driven, and so we lose the essence of this formulation. So let's look. Calamine and zinc oxide are insoluble powder. Arachis oil, self-emulsifying glycerol monostearate, cetamacrogol emulsifying wax, and phenoxyethanol and water are all a part of this recipe. This recipe is a little bit more complicated, but let's look at the next slide. Here, I've tried to break it down for you just to show you. So this is a little bit too complex and we don't really have the raw material to make this in the lab, but it's good to be aware. The arachis oil, the self-emulsifying glycerol, and the cetamacrogol, and even the phenoxyethanol all mix in the oil phase. So even though phenoxyethanol is the preservative, it is compatible with the oil phase, unlike chlorocresol, where we dissolve it in the oil phase. So in putting a sample method together for this, I really had to think carefully about doing this PowerPoint. So let's look at the principle. So I'm thinking that we would mix the powders geometrically because they're two bulky powders, and we'll mix them geometrically in the glass mortar and set them aside, right? Because they're bulky non-powders, insoluble powders. Then you create the melt with the oil phase, which is a self-emulsifying glycerin monostearate, which has a melting point of 55 to 65, and the cetamacrogol melting range is 50 to 55. So I advocate that you melt these two together and keep them at 60. Heat the water phase and maintain at 60 as well. The phenoxyethanol, on closer investigation, type it in ChatGPT, we're the technology age, it says more soluble in the oil phase. So a cute thing that we can actually do is use the arachis oil for the dissolving. So get a beaker, use the arachis oil to dissolve the phenoxyethanol, but take note it's 200 grams. You'll need the density to convert to liquid milliliters so you can easily measure it with a syringe. But bear in mind, you'd have to leave some, yes, even though it's an oil, You leave some to theoretically rinse the beaker, and I recommend that you use a spatula that allows you to scrape and recover the viscous arachis oil from your beaker. This is a little bit tricky because the phenoxyethanol is more soluble in the oil phase. And so I think when I looked it up, it's also a liquid. It comes as a liquid, so you'd merge it with the arachis oil, right? It's not a powder. Now, once you have all these phases merged together, you mix well, merge at 60 degrees, and allow everything to come together. Mix until your cream is formed. Here, for the lab activity, this is where I'm going to leave you. We're down to our last 2 slides. We are going to modify the aqueous cream formulation by adding calamine 2% cream to it. Now, what are the lab write-up that you'll expect to do? I mean, that you can experiment in your own lab so you can get hands-on experience in adding a powder to aqueous cream base. You can do full fusion method where you do your calculation for the recipe, whatever you get for the aqueous cream base, you make the exact amount of base. Once you make your cream base, nice fluffy cream, you scoop off some, levitate the calamine on an ointment slab and scrape up everything and put it back into the crucible and mix it nicely until it's formed. This is the full fusion in situ. Everything is being made in the crucible. Similar to how we do fusion ointment, where you're adding an insoluble powder to a fusion ointment base, it's no different. But there's a version 2. You could actually integrate fusion method to make your base, where whatever your calculation gives you, you make 20% extra of the base that you are expected to make or use. You do your cream, so you made the aqueous cream in the crucible. Once you get that nice fluffy cream, remember you'd have made excess of what you really need, you weigh off the required portion that the prescription calls for and use the incorporation method to finish making the product on the ointment slab. The 2 versions are different because one will be made strictly in the crucible. You're only using the ointment slab to spatulate the powder or levitate the calamine, of which you'll scrape it up and put it back into the crucible where the cream base is already made and waiting for you. Or the second one, the product is being made, the base is being made in the crucible, but you're going to remove what you need by weighing what you need and then using incorporation or trituration method to make your product on the ointment slab. So this is diphenhydramine hydrochloride. We're using the same aqueous cream. DPH would be soluble in the water phase, and so you'd use some of the calculated water to do the dissolving of the DPH and add it to the melt, and reserve some of the hot water to rinse the beaker that would have been used to dissolve your DPH. Now, for this one is the same principle. You can make the exact base and do a full product in the crucible, or you can make extra aqueous cream than what is needed and use incorporation method. The second method actually works for drugs which are heat sensitive, where you would not want to expose the drug in high temperature on the steam bath. So this to me, the version 2, base being made by fusion, adding the drug by incorporation on the ointment slab, making excess base, weigh off what you need, and levitate on the tile, is all driven by the fact that you don't want any heat to destroy your active ingredient. And so that's why that hybrid method or procedure actually works. That takes us to the end of our video, where we explore formulations, pros and, well, thought processes for your method and why we do what we do. And so there will be a 4th video, if time allows, where we look at calculations, strictly calculations, in making a cream formulation. Thank you. If this video was helpful, remember to like, subscribe to the channel, and look for more content like these.